Hi everyone, welcome to today's lesson. Before we talk about Bernoulli's equation, I want to go over the bell ringer because this is a classic physics problem or thought experiment that you may encounter later in your education, and I want you to know the answer for it. Um, and even if you know the answer for it because you guessed correctly, because you had 33.333% chance of guessing correctly, I still want you to know the physics behind it, okay? All right. And it said, a boat carrying a large boulder is floating on a lake. The boulder is thrown overboard and sinks. The water level in the lake, with respect to the shore, A goes up, B goes down, C stays the same. Okay, I don't want to say most of you, but I think some of you chose A goes up because I believe that is intuitively what you would pick. At least that is what I would have picked. Um, I guess. Well, I don't know because I have a degree in this, so I guess that's not fair. Anyhow, I think by intuition it goes up, right? Because we have an object that is submerged in water, so the water level should rise. That is what we know. And to illustrate this situation, I have this is a screenshot. The left side is a screenshot of the simulation. And I have the simulation over here. I don't have a boat nor a boulder, but I have a wooden box and an aluminum cube. And the wooden box represents the boat. The aluminum cube represents the boulder. Okay? Roughly, but it works. To solve this one, the physics principle behind it is Archimedes' principle. And that one said the buoyant force is equal to the weight of the displaced fluid. Weight, this W is for weight, FL is for displaced fluid. Okay? How can we know the weight of the displaced fluid? Well, the displaced fluid is going to be equal to the volume of the object that is, the object or part of the object that is being submerged in water. So for this situation, we have over here this part of the wooden box that is submerged in water. Sorry guys, this is going to happen many, many times, what you saw over here, because of my accent. It is what it is. All right? Shout out to Clay. It is what it is. Okay, so we have this volume, and I happen to know the volume of this part of the wooden box is 2.7 liters, right? So the water level is rising 2.7 liters. Okay? And before we go over what happens, the physics behind what happens, I just want to recreate or do this experiment, right? This simulation. And we're going to move this aluminum cube so that it sinks, and we'll see what happens with the water, okay? Notice the water level is 104.7 liters, and boom, the water level went down 1.7 liters. Why is that the case? Okay. So the answer, the textbook answer is because when the boulder, or you can think of the aluminum cube, is on the wooden box, what's being displaced is the weight of the aluminum cube, and when we let it sink, what's being displaced is the volume of the aluminum cube. Volume, weight. Okay? And I think this is not enough to illustrate what happens. So I will use a thought experiment by means of an extreme case. And I got this, I guess you could say, idea from this YouTube person called the Physics Girl. Obviously, that's not her name, but that's her channel name. So thank you. And it goes like this. Let's say instead of the aluminum cube we could, right, just for the sake of this example, we had tiny bit, right, of a neutron star. This over here, this tiny bit. Told you. Neutron star. Contrast so you can see it. Okay. A neutron star is very, 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 very dense. Therefore, it follows that this is very heavy, even though it has a very small volume because its density is very, very large. Okay. So this is very heavy. Okay. So its weight is very large. Don't forget, weight is the force, which is we can find by multiplying mass times acceleration due to gravity. Now, if I could take this this tiny bit of neutron star and place it on the wooden box, let's just assume the wooden box will not break, right? Then what would happen is, so we take this, we place it on top, and the wooden box just, look what happens to the volume, okay, to the water level. Boom, goes down, right? Because the neutron star is very, 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 very heavy. But then what happens if we move the tiny bit of neutron star and we just let it sink? We do this and, wait, the water level goes down because the volume of the neutron star is so small that it makes almost no difference, right? It makes almost no difference on the water level, right? The water level only has to displace the volume of the wooden box because this is so tiny that it makes almost no difference, right? The volume that is being displaced is a tiny bit, right? Whereas when we have it on the wooden box, well, it makes it sink. So now the water has to, well, the displaced fluid equals the entire volume of the wooden box, okay? So hopefully that example helped a little bit with that extreme case. So let's just try it again, right? 4.7 and it goes down to 103. Okay, all right. Now let's review real quick some of the things we have learned thus far. We had a situation with a container, and we could find its pressure by multiplying rho g h. This is rho, Greek letter rho. This is density, acceleration due to gravity, height. And we call this, or we can use this to find the gauge pressure. This works when you have a sealed container, closed container, no atmospheric pressure, no pressure from the atmosphere is being considered. So this is gauge pressure. And I don't know what's wrong with my pen, guys. Something wrong with it, but that's okay. We'll figure it out. There you go. This works when you have a sealed container, closed container, no pressure from the atmosphere, okay? Now, what if we had an open container, or we are considering the pressure from the atmosphere? But then we have to add P0, which is the pressure from the atmosphere, atmospheric pressure, plus rho g h. This is a better rho than this one. And this we call the absolute pressure. Okay, absolute pressure. Absolute pressure. Man, I'm telling you, this pen is not working. And some people have it as PABS. This is not related to the interlock brake system from your car, but I don't know, I think it looks like PABS, so just let's see if you like that, okay? And, well, this is the variation of pressure with depth in a fluid. This is the same thing with now with absolute pressure. And we also learned about, this is with when fluids are not moving, right? This is static pressure, it's a hydrostatic situation. We also learned that flow rate, wait, let's do it over here. Q, right? It's flow rate. That is equal to volume V divided by time T. This is flow rate. And then by using algebra, we found a different version or a second interpretation of flow rate. Cross-section of area 1 times velocity 1. Don't forget that this weird V, wait, not 1, right? Sorry, that was my bad. So just cross-section of area times velocity. And I keep adding the 1, just times velocity, okay? This is velocity. Don't forget that I'm using different V's so that we don't get this one confused, volume with velocity, okay? And one of the most important things about flow rate is that flow rate man, this is stressing me out. Flow rate is constant. Okay, this is super important. Sorry about the way this is working. Hopefully this fixed the pen. Okay, flow rate is constant. Now, let's say we have this situation, right? We have cross-sectional area 1, cross-sectional area 2. From the fact that flow rate is constant, that is flow rate at section 1 equals flow rate at section 2, we can combine this and this to then say flow rate 1 equals flow rate 2, which then we can rewrite cross-sectional area 1 times velocity 1 equals cross-sectional area 2 times velocity, let's try that V again, velocity 2. And this is what we call continuity, patience, continuity equation. Okay, where were we? Yes, continuity equation. And this helps explain, so let's say we have here a cross-sectional area, right? We already have the first one, which is this on the left side. So we have cross-sectional area 2 over here, right? Cross-sectional area 2. There you go. And then we'll have some red fluid, maybe Kool-Aid, could be whatever you want, that has the color red. We have many molecules of this fluid, right? Oh, let's do one more over here. And then we have 1, 2, 3. Okay. We know that the flow is to the right. That is, maybe we can kind of like show it like that, right? That's how the flow is going, that direction. And we're going to take this molecule and say it has some velocity, right? We're going to call this velocity 1. So velocity 1, the reason why is this is cross-sectional area 1. Let's call this cross-sectional area 1. And then we have, this is cross-sectional area 2. And hopefully you remember from the simulation that the velocity here is greater than the velocity at section 1. So this is velocity 2. Okay, kind of looks like the square root of 2, huh? Let's try to fix it. Let's try to fix it. So velocity 2. Okay, and I think this is simple to see. Let's talk about the pressure. Okay, maybe you saw it when you were playing with the simulation. Maybe you didn't. But let's do a thought experiment, and let's present an example. Let's say we are, and by we I mean a lot of people, right? A lot of students at Bridges. We have a lot of people, and we're at the small gym, and it's packed, right? It's packed. And if I ask anyone, hey, run to the other side of the gym. Well, running would be hard, something hard to do because there's a lot of people, right? There's a high concentration of people. Therefore, you cannot just move freely and run to the other side, right? You can't move to the other side that fast because you're going to bump into a lot of students because you have a higher concentration of students. Now, let's say we have a smaller area. Let's say we're in my classroom, but there's only like 3 people there. If I ask you, go to the other side, run to the other side, you could probably sprint, do it very, very fast because there's a very low concentration of people, even if you have a smaller space, right? And that's why over here, section 1, let's call it pressure 1, and over here, let's call it pressure 2. Well, pressure 1 is greater than pressure 2. There's a higher concentration of molecules, fluid molecules. There's a larger concentration of fluid, and it has to move slower, right? And this is a smaller area, smaller concentration, therefore higher speed. Okay, that's why. And if you guys remember the first question we asked for the continuity equation lesson, which said, what happens to a garden hose when you pinch the nozzle? And we said, oh yeah, it goes faster, reaches farther. Some people say we have an increase in pressure. Well, no, we have a decrease in pressure, actually. I think it's counterintuitive, but now you know, right? Low pressure, high velocity, and high pressure, low velocity. Okay. Well, now we are going to look at a way of combining all these: area, pressure, velocity, density. And it starts with the fact that we have a change in velocity, right? So we have velocity 1, velocity 2, and it's increasing. If you have a change in velocity, you have an acceleration. If you have an acceleration, there was a force. And well, what is applying that force, right? We don't have like a device, a piston, or something that is applying a force over here. So why do we have an acceleration? Well, we know that pressure, right? Pressure equals force divided by area. Okay? You have area, pressure. And the change in pressure, the pressure difference, right? There's one pressure over here, and there's another one over here. That change in pressure or pressure difference, that causes the acceleration. Okay, you have a difference in pressure, then it results with a force in acceleration. Okay, so the difference in pressure yields or causes this acceleration. Now, if we have a force, right, well, we have a change in pressure, then the velocity is changing. We can say that the energy is changing too, right? You have a moving fluid, it has to have kinetic energy, okay? And let's recall the energy conservation, right? That in a system, the total energy, so energy total, total equals potential energy. Let's just say gravitational for the sake of argument. Just gravitational. Let's say we don't have a spring plus the kinetic energy of the system, right? And within the system, this is always going to be constant, right? Constant. Well, you probably guessed, but energy conservation applies to fluids because we have a moving fluid, okay? And this is something that Bernoulli, Daniel Bernoulli, I don't know if his name's pronounced Daniel, I'll just say it because that's the American way. Bernoulli came up with this. So he said, based on energy conservation, if you get the, let's say we select this location over here, right? This location. The pressure at point X, over here, will be the pressure, the energy, right, of the fluid would be the pressure at that point plus the potential energy of the fluid. Well, how do you know the potential energy? Well, the potential energy, the normal formula is mgh, right? Well, for fluids, instead of mass, we use density. Look at this, right? mgh, rho gh. So let's try that rho again. Plus the kinetic energy. So this is 1/2 mv squared. Instead of mass, we use density, so 1/2 density times velocity squared, and that is always constant because of energy conservation. So Bernoulli's equation is energy conservation applied in fluids, okay? Bernoulli's equation is energy conservation applied in fluids. So now let's change let's expand this equation, and we're going to compare two sections, right? So let's title this Bernoulli's equation. Bernoulli's equation. Bernoulli's equation. So write it down, guys. It is very important. Okay. There you go. Now let us consider this pipe, right, with different cross-sectional area. As you can see, there's something on my screen. Oh, it wasn't on the screen, it was on the actual thing. Okay. So let us consider this pipe. As you can see, we have different cross-sectional areas. So let's have them over here. Let's say this is cross-sectional area 1. There you go. And then we have cross-sectional area 2 over here. There you go. And there you go. Okay, you can see a higher concentration, lower concentration of the fluid. Okay, let's label everything. So this is cross-sectional area 1. And I'm just going to label it as A1. And this is cross-sectional area 2. Okay? And now we have to consider the height. Okay? And the cool thing is we get to pick a reference line from which the height will be decided, right? So this is my reference line, and anything going up will be an increase in height. So if I were to pick here, this location, right? So let me draw this height. So I'm going to pick here, from here to here. I would call this one height number 1. There you go. Let me fix this real quick, guys, so that the example makes sense. So this is H1. I don't know if that looks like an H. Let's try it again. Come on, I can do this. H1. And I'm going to pick over here to be my second height, H2. I need to add endpoints, right? So H1 goes from here to the reference line. H2 goes from here to the reference line. So now we have 2 different heights. This is H2. Okay. Well, not only we have different heights, but we've had different velocities, right? So we have this one with velocity v1, and then we have this molecule with velocity v2. I'm exaggerating the velocity, but it's fine. Just so we know they're different velocities, right? So this is velocity 1. Let me change the color, right? So we have a bit more contrast. Let's go for green. No, it's even worse. Black. Velocity 1. And this over here is velocity 2. So have different velocities. And we have different heights. And of course, different pressures. So pressure 1 will be on this side. Man, green is not a good color for this. And this is pressure 2. Okay. So now we can take this Bernoulli's equation and compare it in section 1. This is section 1. This is section 2. So I'm going to rewrite this equation, but I'm going to use a subscript of 1, right? So at section 1, I'm going to have pressure 1 plus the potential energy. Now, we're assuming the fluid cannot be compressed, it's incompressible, and it keeps the same density, right? So it'll be rho, acceleration due to gravity is a constant. We have height 1 plus the kinetic energy. So 1/2, the density is the same. Velocity 1 squared. That should be equal to the energy of the fluid at section 2, which is pressure 2 plus density is the same. Acceleration due to gravity is the same. Height is different. Height 2 plus 1/2 rho v2 squared. This is the long version of Bernoulli's equation, guys, okay? And what I want to add, so I'm going to move this one over a little bit. I want to add something to this top one. That way it makes sense to you. So this over here is the pressure. So I'm going to add all the arrows first, and then I'll write the text. Okay. There you go. Let us add the text. So this is the pressure. Some people call it pressure energy. I don't want to do that. This pressure. This is potential energy of the fluid. And this is kinetic energy of the fluid. Okay, and this is Bernoulli's equation, long version. Make sure you write it down. It is very, very important. Super important. Okay? And luckily, we don't have to use this whole thing because it looks kind of scary. But I mean, I don't think it's that scary. Just pressure, potential kinetic energy on one side equals pressure, potential kinetic energy on the other side. Lucky for us, we have two common cases, situations where we have, we can simplify Bernoulli's equation. So the first one is Bernoulli's equation at constant velocity, or when you have static fluids that are not moving, okay? Okay, so here's the simulation, and so we need to get the speed, right? It's equal speed, but we need to have different heights. So I'm going to move this one, the whole thing. There you go. There you go. And I'm going to move this one over here. Right, different heights, as you can see. Okay, well, I'm going to set this as my reference line. And we have equal velocity, but let's say we pick this location. This one is at about 2 meters, right? This is the height that I'm choosing. And then this velocity is at about 3 and change meters. Okay, different height, equal velocities. Okay, so velocity 1 equals velocity 2. Okay, velocity 1 equals velocity 2. Okay, how does that look? Well, let me get this thing going on, guys. Sorry about that. There we go. We know that velocity 1 will be equal to velocity 2. I'm going to copy Bernoulli's equation. I don't want to write it again. Let me make sure I get the square, because sometimes I miss the square. Right, I'm going to use it over here. So if that's the case, if velocity 1 equals velocity 2, then this kinetic energy will be the same as this one, right? Because you have the same velocity, therefore this number is going to be the same because you have equal density. And we can just cancel this one and this one. So the Bernoulli's equation at constant velocity, or when you have static fluids, is simply pressure 1 plus rho g, let's try that rho again, rho g h1, because you have different height, equals pressure 2 plus rho g h2. And if this one looks familiar, well, of course, this is the absolute pressure over here, right? Different version of it. Okay, so that is Bernoulli's equation when you have a constant velocity at a constant speed. Sorry, a fluid at constant velocity, or when you have a static fluid. Okay, so now let's go for Bernoulli's equation when you have a fluid at constant height. So let's add the reference line. This is my reference line. It'll be here exactly at this point. There you go. And I'm going to pick a velocity. Well, let me draw the line first, right? Because that way I know they're at the same height. So I'm going to draw a line here. There you go. This is almost, I think this is straight, okay? Then I will add the cross-section area over here. A little bit more. There you go. Okay, that's my cross-section area too. And of course, I know I'm going to have some velocity. This fluid is going to have some velocity over here, which I'll call this one V1. Velocity 1. And then my other side, the fluid will have a greater velocity, which we will call velocity 2. There you go. Okay. So now let me add, oh wait, I didn't write H1 over here. Let's go for, this is H1, height number 1. Let's do a better job for that one. Height 1. And we know that height 2 will be the same, and we can see it over here. This is H2. There you go. And then we have pressure 1 on this side, pressure 2 on this side. Okay. So if we copy Bernoulli's equation again, because I don't want to write it all over, it's a long one. Okay, there you go. Well, I know we can, if the height is the same, right? The density is the same, acceleration due to gravity is constant, therefore the height, when then the height is the same, we can cancel this one and this one, the potential energy on the fluid. And we have this very convenient formula, which is pressure 1 plus the kinetic energy, 1/2 rho V1 squared plus, sorry, not plus, equals pressure 2 plus 1/2 rho V, oh, what happened with that V? Last one, V2 squared. That is Bernoulli's equation when you have fluids at a constant height, okay, as you can see. And that is it for now as far as Bernoulli's equation. Well, me showing how to use it. The next video will be this example. Okay, see ya.